Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. This module is on pipelining and how pipelining is getting implemented in the MIPS architecture. So this module is to discuss the basics of pipelining and show how the MIPS pipeline is implemented. So when we looked at the general implementation of the MIPS architecture without a pipeline, that is a single cycle implementation, we pointed out the drawbacks of it. In a single cycle implementation where we assume that the CPI is 1 and all instructions get executed in one clock cycle, obviously the clock cycle has to depend on the longest instruction. So, for example, if you have to assume the critical path for all the instructions, and for the subset of instructions that we have looked at, the load instruction has the longest delay. So, you will have to have a clock cycle which is long enough to accommodate your load instruction. And this is not possible when you have a variation of instructions. When you have similar type of instructions, this type of implementation is possible. But when you have varied types of instructions like floating point operations, which are very complex to implement, it is not obviously feasible to go in for such a design because a lot of time will be wasted and performance gets affected. So, this also violates our basic design principle of making the common case fast, because there is no point in making the common case fast because you will have to go by the worst case delays. So, in order to improve the performance of this single cycle implementation, we will have to give up the single cycle implementation and look at what is called pipelining, which is a multi-cycle implementation. Now, first of all, we look at the basics of pipelining and then we look at how a pipeline is implemented in your MIPS instruction unit. So, what is pipelining? Pipelining is basically overlapped execution of instructions. Say for example, in order to draw an example from your day-to-day life, if you have visited the assembly line of an automobile manufacturing unit, you find that there are multiple stages in your assembly line, and an automobile enters one stage of the assembly line, has some job done there, then it automatically moves on to the second stage of your assembly line. Now, the first stage of your assembly line is free to take up the next automobile. So, when the assembly line gets filled up, you find that multiple automobiles are available in the assembly line, each one undergoing one particular process. So, that is your overlapped execution of operations. Once the first automobile unit finishes the last stage of assembly, it rolls out, and once that rolls out, the next one enters the last stage, and once that finishes, that also rolls out. So, the time that each automobile remains in the assembly line does not change. It still has to go through all these stages, but the throughput obviously increases. Now, that is the concept of pipelining, and the same concept is going to be adopted for our instruction unit also. So, we are going to have an overlapped execution of instructions and we are going to have an increase in throughput. So, the latency of a single instruction does not increase, it is a throughput that is going to be increasing. And this is one way of introducing what is called instruction level parallelism in a sequence, in a single processor. So, there is only one processor, but within the processor, within the instruction unit of the processor, we are trying to have overlapped execution of instructions, which means multiple instructions are going to be executed simultaneously, and that is how we introduce instruction level parallelism here. Now, this is an example from the laundry that we do day-to-day laundry. Let us assume that 4 people have one load of clothes to be washed, and let us assume that there are 3 processes here, a washing process, a drying process and a folding process. So, the washer takes about 30 minutes of time, the dryer takes 40 minutes of time, and the folder takes 20 minutes of time. Now, if you look at a sequential laundry, if all 4 people have to wash their clothes, then the first person takes 30 plus 40 plus 20 minutes to finish the whole process. So, that is 90 minutes. Then after that the second person finishes, after that the third person finishes, and after that the fourth person finishes. So, in order to finish 4 loads of clothes, finish washing all the 4 loads of clothes, it takes about 6 hours. Now, suppose instead of looking at a sequential operation like this, if we look at a pipelined operation, what will happen? So, when one person has finished washing and the other person moves on to the drying unit, the washer is now free. So, the washing of the second person can be overlapped with the drying of the first person. Now, all this can happen provided you have a separate washer, a dryer and a folder. So, you have a pipelined execution here. So, you have overlapped activities taking place. Say for example, here you have simultaneously 3 activities taking place, simultaneously 3 activities taking place. So, your pipelined laundry does not take 6 hours to finish for 4 loads, it takes only 3.5 hours to finish. So, if you look at the speed up between a non-pipelined laundry and a pipelined laundry, you find that the speed up is 6 by 3.5, which is 1.7. Now, this is for 4 loads of clothes. Suppose if we assume that you are going to do this process non-stop, then you know for n number of loads of clothes, it is going to be 110n divided by 40n. Why 40n? Because that is decided by the slowest unit, because even if your drying finishes in 20 minutes, the next unit will be available. The previous unit, the dryer unit, is going to take 40 minutes to finish. So, only then it is going to come to your dryer unit. So, you will have to go by the slowest unit. So, that is 40 units, and the 70 is for the initial time where your pipeline gets filled up, because till your pipeline gets filled up, you are not going to do overlapped operations. So, that is for your pipeline to get filled up. So, if you calculate the speed up here, it is approximately equal to 3, which equals to the number of stages in your pipeline. So, if you look at a pipelined execution, the speed up is ideally equal to the number of stages in your pipeline. It is only ideally equal to the number of stages in your pipeline. So, if all the stages are balanced, because you know that even if one stage is going to take a lot of time and all the other stages are going to be very fast, but this stage is going to be a bottleneck, because every instruction or every unit will have to move through this stage. So, if that stage is going to take a lot of time, then the whole process gets delayed. So, the speed depends only upon the slowest of the units, and you will have to have stages being balanced. If one stage takes very little time and another stage takes long time, then it will again depend only on the one that is taking the longest time. So, it will have to be balanced. So, if all your stages are balanced, that is that they take the same amount of time, then the time between instructions for a pipelined execution is equal to the time between instructions non-pipelined divided by the number of stages. If your stages are not balanced, then the speed up is going to be less, and the speed up here is only due to increased throughput. The latency or the time for each instruction obviously does not decrease, because each instruction will have to anyway go through all the 5 stages of execution. So, the latency remains the same, it is only an improvement in throughput that we get. So, the lessons that we learn from pipelining are: pipelining does not help latency of a single task, it only helps the throughput of the entire workload. Similarly, pipelining rate is limited by the slowest pipeline stage. So, that is why we say that all stages should be balanced and they should take the same amount of time. And you find that multiple tasks operate simultaneously, and it exploits parallelism among instructions in a sequential instruction stream, and the potential speed up that you can get depends upon the number of pipe stages. Unbalanced lengths of pipe stages reduces the speed up, and time to fill the pipeline initially and time to drain the pipeline towards the end reduces the speed up, because you do not have all the units being active during the period of filling up and during the period of draining the pipeline. So, now we will try to apply these concepts of pipelining to a MIPS pipeline. The MIPS implementation, which we have already seen, where it has 5 different stages of execution: an instruction fetch, decode, operand fetch, where you read it from the registers, and then you have an ALU operation which happens depending upon the type of instruction to be executed. Then you have a memory access happening for load and store instructions, and the last stage of write back, where the data is written back into your register file. So, now if you look at a pipelining getting implemented here, you can look at 5 stages, 1 step per stage. So, the first one is your instruction fetch, where the instruction is fetched from memory. The second one is instruction decode and register read. The third one is execute the instruction or calculate the address depending upon what instruction it is. The fourth one is the memory access, which happens for load and store instructions, and the fifth one is writing the result back to registers. So, if you look at the pipeline performance for a MIPS implementation, assume that it takes 100 picoseconds for register reads or writes and it takes 200 picoseconds for other stages. We will try to compare the pipeline data path with the single cycle data path, which we are already familiar with. For a load instruction, it takes a total of 800 picoseconds. For a store instruction, again it takes 700 picoseconds because it does not need the final register write. An R format instruction takes 600 picoseconds and a branch on equal instruction takes 500 picoseconds. So, if you look at a pipeline performance here, for a single cycle implementation, each instruction takes 800 picoseconds because it has, if you look at 3 load instructions here, the first load instruction takes 800 picoseconds, the second instruction takes another 800 picoseconds, so on and so forth. But if you look at a pipelined implementation, now the instruction fetch happens for the first instruction, and when this goes into your decode and register read, the second instruction fetches happen. So, the instruction fetch of the second instruction and the decode and register read of the first instruction gets overlapped. So, this is an overlapped operation of instructions, and this is decided by means of the longest unit here. So, you have a pipelined implementation here and it takes 200 picoseconds for implementing this pipeline, the slowest stage. So, if all stages are balanced, you find that time between instructions is time between instructions non-pipeline divided by the number of stages. So, if it is not balanced, as I pointed out earlier, the speed up is going to be less. Ideally, the speed up is equal to the number of stages and the CPI for a pipeline implementation is 1 because every instruction is going to finish in 1 clock cycle. So, the CPI value is 1 if you look at an ideal implementation. So, if when you are looking at pipelining and how your ISA will have to be designed in order to be pipeline friendly, MIPS architecture is an example of a pipeline friendly ISA. So, if you look at the MIPS ISA, all instructions are 32-bit instructions, which means the time taken to fetch an instruction is going to be the same whatever instruction it is. Now, compare that to an x86 architecture ISA where it has instructions varying from 1 to 17 bytes. So, depending upon the instruction, it may take different times to fetch the instruction, and depending upon the decoding that happens, you have a complicated decoding process in the case of x86 architecture. So, the decoding also is going to be difficult there and it is going to be varying. Whereas, when you are looking at a MIPS implementation, it uses a fixed length instruction format and it uses fixed encoding. So, you find that the decoding time is the same for all instructions in your MIPS architecture. Similarly, if you look at the instruction formats, you have few and regular instruction formats. So, the opcodes are always available in the same place. You have only one level of decoding to be done. So, all that gives you uniformity with respect to all instructions. And it is a load store ISA, which means only load and store instructions will have to access the data memory. So, the address is calculated in the third stage during your ALU stage for a load store instruction, and the memory access happens in the fourth stage. And because all memory operands are aligned memory operands, you find that the memory access takes only one cycle. So, if you look at the MIPS ISA, you find that it has a lot of features which are very pipeline friendly. So, pipelining gets implemented very easily when you go in for a MIPS ISA. Whereas, when you look at a complicated instruction set ISA, you will find that the instruction lengths may vary, the decoding may vary, and many instructions may look at addressing modes which will try to access operands from memory. So, all this will complicate your pipeline implementation and you will not have a balanced pipeline. So, this is the MIPS data path implementation. As you can see, this is the MIPS data path implementation. So, the flow is from right to left to right. Whenever you have a right to left flow, that leads to hazards. So, the first part is your instruction fetch, where using the program counter you are accessing your instruction memory and you are getting the instruction. The second part is your decoding part, where the instruction gets decoded and you read from the registers, you take the immediate operand, sign extend it and use it for the next cycle. The third phase is your ALU operation. For all ALU operations, it either takes the register operands or it takes an immediate operand along with it and calculates the effective address, does an arithmetic operation or calculates the target address for a branch instruction. So, all that happens in the third phase. The fourth phase is a data memory access, which happens only for load and store instructions, and finally you have the memory write back, data write back, where it is written into your register file. So, this is your MIPS pipeline data path. So, the pipeline stages have been indicated using lines. Now, in order to implement this pipelined implementation, go in for a pipelined implementation, what becomes mandatory is the registers that have been indicated here as bars. So, once an instruction has been fetched from memory, that instruction with all its associated information is written into this buffer. So, the next stage takes the information from the buffer, operates on it and writes it into the next buffer. Now, what you have to remember is, as there is not just one instruction which is moving in your instruction unit as in the case of a single cycle implementation. In the case of a single cycle implementation, during the entire course of this instruction execution, there is only one instruction being executed in your instruction unit. So, at any point of time you can go and fetch the data with respect to that instruction from anywhere in your instruction unit. Now, that does not hold good anymore. So, as you go in for a pipelined implementation, each phase of your pipeline or each stage of your pipeline is executing a different instruction. So, you can't expect a stage to hold the information about the previously executed instructions. So, an instruction as it moves down the pipeline, it has to carry with it along with it all the instructions all the data that is needed for it. So, an instruction finishes the first stage, writes into the buffer, at the next cycle, next stage it takes the information from the buffer, performs some operation and writes it into the next buffer, so on and so forth. Say for example, when an instruction reaches a write back stage, you will have to take the data only from this buffer to decide where to write back. You can't go back to your instruction register and try to get the details about that instruction. So, the pipeline registers or buffers become mandatory for implementing a pipeline. So, the cycle by cycle flow of instructions through the pipeline data path, you can show it in different ways. You can show a single clock cycle pipeline diagram or you can show it as a multi clock cycle diagram. We look at a single clock cycle diagram for load and store and then we look at the other type of diagram also. So, this is the instruction fetch for a load store. So, as you can see, you have your instruction fetch happening here. So, the program counter which takes the value from the mux, it would have had the value. So, that is used to access your instruction memory. So, the instruction that is being accessed is written into this buffer during the first phase of your pipeline. And then when you go to the next phase, where you have to decode and read the register contents, this stage takes the data from this buffer, performs register reads and writes it into this buffer. So, these are the functional units that are active during this stage. But recall that when this instruction is undergoing a decode stage, the next instruction will be doing this stage where it will do an instruction fetch. So, as part of an instruction fetch operation, you will have to update the PC appropriately. So, that updated PC value will be used during that cycle to fetch the next instruction. So, if you look at the next clock cycle, you find that data is taken from this buffer, execution happens here and then that is written into the next buffer. So, this is for a load operation. Similarly, if you are looking at a memory write operation, data memory access operation here, the data memory is being accessed here. So, from this buffer you take the address, access the data memory, the data becomes available and the data is written into this buffer. That is your memory access cycle. And the last cycle is of course your data write, where to do your data write operation, you will have to use the last stage of your pipeline. So, the data, the address is taken from this buffer. The data to be written either comes through this line or comes from here, and finally it is written into your register file here. So, it has to go to the register file. But recollect that when you are writing into the register file, the which register to be written into is taken from this data. So, you can't have this data because this unit is doing some other operation. This stage is executing part of some other instruction. So, that also has to come from the buffer here. So, that is shown in your next instruction. Otherwise, it will show the wrong register number. So, for write back, you have the address here, the data here. So, you are trying to write it, but you should know which register to write it. That information is also available only in this buffer. So, that buffer transmits the data here. So, from this buffer, you move on the data to this register file. So, in essence, indicating the fact that as an instruction moves down the pipeline, all relevant information will have to move along with it in the pipeline. So, when an instruction reaches the write back stage, everything relevant to the write back operation is available only in this buffer. You can't expect it to take it from any other buffer. Similarly, if you are looking for an execution for store, the first two stages remain the same. For a store operation, you have to calculate the effective address, and then you will have to write into your data memory. So, store finishes there, you do not have a write back cycle for your store. Write back for store need not have to have a write back for store because store finishes with the memory access. If you are looking at a multi-cycle pipeline diagram, this shows what happens during the multiple clock cycles of your execution. This basically shows you what resources are being active. So, clock cycle 1, you have the instruction fetch happening. Clock cycle 2, you have the instruction fetch of the second instruction and the decode of the first instruction happening. Clock cycle 3, you have the instruction fetch of the third instruction, decode of the second instruction, and ALU operation of the third instruction happening. So, during the fifth clock cycle, you find that all 5 stages of the pipeline are filled up. So, that is basically showing a multi-cycle pipeline. So, this is again showing it in a different form, indicating the various operations that have to be done. So, if you look at a single cycle pipeline diagram, the same as we discussed before, that shows you all your stages for each and every instruction, what are the various stages that happen. So, now we have looked at the data path implementation. Now, what about the control signals for a pipelined implementation? So, for a pipelined implementation also you need to have control signals. Just like how we had the control signals generated for a single cycle implementation, you need to have control signals being generated for your pipelined implementation as well. So, when your instruction gets fetched from memory and once it gets decoded, all the control signals will get generated. Say for example here, so the instruction fetch happens, and once your instruction is decoded, it goes to the control unit and the control unit generates all the control signals. But one thing that you have to remember is all the control signals are getting generated here, but all the control signals are not needed for only one phase. Some control signals are needed for the execution phase, some control signals are needed for the memory access phase, some control signals are needed for the write back phase. So, the control signals that are needed for the execution phase are immediately going to be used, and the control signals that are needed for the next phase, namely the memory access phase, are going to be transmitted from this buffer to the next buffer here, and they are going to be used here. The control signals that are needed for the last stage, namely the write back stage, are generated here, they are moved here to this buffer, and from there they are moved to the next buffer here, and they are going to be used in the write back stage. So, the control signals get generated at one point, but they move along with the instruction as the instruction moves through the pipeline, and they are used at the appropriate stages. So, this is the general diagram of a pipeline control showing the data path implementation as well as the control implementation. So, we have seen this is the instruction fetch that happens here, instruction fetch where your program counter is used to access the instruction memory, and it is written into the instruction buffer, and from there it is decoded. Once the instruction is decoded, it also goes to the control unit. The decoded instruction goes to the control unit. It generates all the control signals. You have three categories of control signals, one to be used during the execution stage, one to be used during the memory access stage, and one to be used during the write back stage. And then you also have the same control signals indicated here. So, for example, a register write control signal which tells you when you will have to write into the register, a read register signal which tells you which registers are to be read, a sign extension unit, all that is the same as before. So, and the next stage is doing the ALU operations. For example, if you look at the execution unit, one control signal that is generated is the ALU source, which tells you whether you have to take the register contents as part of the input to the ALU or take the sign extended value as part of the ALU. That is an example of an ALU source. Similarly, another execution control signal is your ALU op, which tells you what ALU control signal is to be generated. So, those are examples of the execution phase control signals. So, if you look at the memory access control signals, that will tell you whether you have to perform a memory write or a memory read, depending on whether it is a store instruction or a load instruction. A branch instructions control, if you assume that the branch gets resolved at this point, it tells you whether the branch is satisfied, the condition is satisfied or not. Similarly, if you look at the write back control, that tells you when the write back has to happen. A register write control signal is indicated here. It also tells you which data is to be written, whether it is the data that comes from the data memory as in the case of a load instruction, or the data that comes from your ALU unit as part of your arithmetic operation. And recollect that the feedback path here indicates which register is to be written. So, when you look at a write data, not only the data has to be written from the last unit, it is also the write register signal which has to come from the last unit, because only this buffer, the last buffer, contains information about that instruction. So, this shows the complete pipelined control. So, in order to summarize, we have looked at the basics of pipelining. Pipelining is the overlapped execution of instructions. So, once we know that a single cycle implementation is not going to give you the required performance, you will have to decide to split your instruction into different phases, and we try to look at overlapped execution of these instructions. So, different instructions get executed parallelly. So, every instruction goes through the same phase of instruction fetch, decode, register reads, execution, memory access and write back. So, the latency of each instruction is the same, but it is only the throughput that improves, and the throughput basically depends on the speed up that you get depends upon whether the pipeline is balanced or not, and whether you have other problems in the pipeline which we have not pointed out, which we will discuss in the later sessions. So, the pipeline rate is limited by the slowest pipeline stage. So, even if you have all units working very fast and there is one slow unit, because every instruction will have to move through that slow unit, the slow unit will decide the speed of the pipeline. So, you cannot have an unbalanced pipeline that will bring down the speed of the pipeline. An ideal speed up that you can expect will depend upon the number of pipeline stages, and ideally your CPI value will be 1. And we have also looked at how pipelining can be implemented in the MIPS architecture for the simple subset of instructions that we have considered for the MIPS architecture. Thank you.